This is CPM Precalculus Chapter 2, number 89. Find the domain of each function. Okay, so a quick talk about domain. We know that given a graph, right, we know the domain is all of the x values, right, that give us a y value. All x values that give or produce a y value, right? So if my graph looked something like this, right here, and maybe that's -1, and maybe it's like this to the right. If that's my graph, right, then I can say my domain, I could basically take horizontal lines here and say I have, for all these x values over here, I have a y value output, right, because it hits my vertical lines, it hits my graph. So then from -infinity, and it stops here at -1, right? And I'm excluding -1 because it never passes this asymptote, right? And then it's going to start again at 1, but not include 1 because it's an open circle, and go to the right to infinity, right? Because vertical lines would go ahead and yes, these all have a y value, all the x values. So the only x values that don't are between -1 and +1, right? Okay, so that's looking at it graphically. So we know how to do that. Well, algebraically, when you think about domain algebraically, right, we're talking about domain. Domain algebraically, we just have to consider when is a function undefined, right? Or when is a function imaginary, right? If we plug in an x value that makes something undefined, this will not give us a y value. For example, if I have 1 over x, right, and I say, what value will make this undefined? Well, x equals to 0 will make it undefined. So that is going to be excluded from my domain. Any other value of x will make it defined, right, except for x equals to 0. So it's going to be from -infinity, stopping at 0, excluding 0, and starting in 0, excluding 0 to infinity. That would be the domain of this. Imaginary. Well, imaginary is when we deal with the square root, right? So if I look at the square root of x, right, this is going to be imaginary, right, when x is negative. So x is less than 0 is when it's imaginary. So I want to remove that from the domain, right? So the domain of this square root of x is basically going to start when we're equal to 0, right? Starting at 0 and to the right to infinity, right? And if you look at these graphs, square root of x looks like this, right? And so you can see the domain starts at 0 and goes to the right. 1 over x is going to look like this, right? Like this, right? With an asymptote here vertically at x equals to 0, and that's our domain. So let's go ahead and look at problem 2, number 89, algebraically, because we know how to do it graphically, and we can use our calculator to graph it and look at the domain. But let's go ahead and look at these algebraically. So here, part A, we're given f of x is equal to 5 over x plus 2. So do we have any reason to say if we plug in a value in x where that would make this imaginary? No, because no roots, no even rooted roots. Okay, so no imaginary, but will the denominator ever equal to 0? Well, we know the denominator equals to 0. Denominator equal to 0. We know x plus 2 is the denominator, and that equals to 0 when? So let's solve for x. Subtract 2 from both sides. We get x is equal to -2. So we know this function is undefined when x equals to -2. Therefore, the domain, right, is going to be everything except for -2. So it's going to go from -infinity all the way to -2, but not include it. So I'm going to use a parentheses, right, because we're not including negative 2. And then it's going to union with starting at negative 2 again and everything to the right. Okay, so that is the domain of our function here. Okay, it's everything except for when the denominator is equal to 0. So we want to remove x equals to negative 2 from the domain. Right? And we've seen something like this. You could also say the domain is just everything, negative infinity to infinity, except x can't be not equal, right, to negative 2. You could even write it like that, right? This is going to be a more clear version for set notation. This one is just going to say all real numbers, right, negative infinity to positive infinity, except for x cannot equal to negative 2. So either of these mean the same thing. All right, let's go on to part B. Here we're given f of x. Our function is the square root of 3 minus x. Okay, and again, we know that that square root, we can even write the 2 here. It's always invisible, right, for a square root. That's the same thing. This 2 is invisible and implicit here. Okay. Whenever we have an even power, though, we know that what's inside will become imaginary when it is negative, right? So in an even root, right, when it's less than 0, we know it's imaginary. So 3 minus x, which is in the even root, when it's less than 0, we know this value is imaginary, and that means it's not going to be real. So let's go ahead and solve for this, getting x alone. So let's add negative 3 to both sides. These cancel out, and we get negative x is less than negative 3. How do we get negative x without the negative? Well, let's divide both sides by negative 1. These are going to cancel. You're going to get x. And remember, when you have an inequality and you multiply or divide by a negative, you have to switch the sign direction. So instead of less than, it's now greater than. And negative 3 divided by negative 1 is positive 3. Okay? So this tells us our domain has to be where x is greater than 3. Okay? Because we do not want this to be the case. We do not want it to be less than 0. So that means x has to be greater than 3. I just said the opposite. We do not want x minus, we do not want 3 minus x to be less than 0, right? We solved for x, get alone. We do not want this in our domain, right? So I can even draw a little quick picture, right? X is greater than 3, so that's here at 3. Oops. I don't know why that did that. So here's 3. X is greater than 3 is everything to the right, right? Open circle because it doesn't have equals. So we do not want this part to be in our domain. So what do we want in our domain? We want the opposite. We want everything to the left, right? And including the circle, because this is not including it, so we want to include it. So our domain is going to be then, right, is going to be starting at negative infinities all the way over here, all the way, and we stop at 3. So our domain is negative infinity, stopping at positive 3, right? And we're going to use a bracket here because this is closed circle. Okay? So again, remember when we're finding the domain, we're going and we have an even root. We do not want inside an even root to be less than 0. We do not want this. So we want to exclude this from our domain. So we want to exclude this part from our domain, meaning it's everything else, right? So this is the domain of this function f of x in part B. All right, let's go on to part C. Part C, we're given another function, right? And ask the same question. Are there any even roots, right? Do we have like the fourth root? Do we have the square root? Do we have the the power of 1/2, that's the same thing, right? So do we have an even root? If we do, we have to make sure what's inside the root, right? If it's less than 0, we want to exclude that from our domain. Here we don't have any roots, but we do have as a denominator. So denominator, we want to go ahead and exclude from our domain where the denominator equals to 0. Where our denominator, right, is equal to 0. So our denominator here is x squared minus 1. So where is it equal to 0? Let's go ahead and solve for this and then exclude that from our domain. Add 1 to both sides. X squared is equal to 1, right? Solving for x, let's square root both sides. Remember, if we square root a square, we're going to get our answer in plus or minus. So x is equal to plus or minus square root of 1. Well, we know square root of 1 is just 1, so that's equal to plus or minus 1, right? So again, we want to exclude where this is true. Remove this from our domain. Okay, so we always start with the domain being negative infinity to positive infinity, including everything, and let's just remove x equals to 1. So if we were to look at the timeline, we just want to exclude plus and minus 1, so negative 1 and 1. We want everything else but this in our domain. Okay, so what is the domain going to be then? It's going to start at negative infinity, going all the way to negative 1. Negative infinity to negative 1, but excluding it, so using a parentheses. Union, then we're going to start again in between negative 1 and 1. Negative 1 all the way to 1, right? Excluding both points, though, because we're not including the point x equals to 1 or negative 1. Union, and then starting again at 1 and going all the way to infinity, right? So we're looking for our domain is everything except these 2 points, okay? And again, you could write it another way. Since you're just excluding something, you could say the domain, the domain is negative infinity to infinity, except we're going to say x cannot equal to plus or minus 1, right? That's another way to say it, but this is the more standard and customary way to say it in set notation. All right. So that's the domain, and I abbreviate it with a capital D. Let's go on to part D. All right. So part D, we're given a function f of x is equal to x cubed plus 7. All right. So remember, we're looking for any even roots because we know inside an even root cannot be negative. Remove negative from even roots. We're looking for denominator, and we remove where the denominator is equal to 0, right? So what is the denominator here? Well, that's just all over 1, right? There is no denominator per se. It's implicitly 1, right? Or this is over 1 and this is over 1, but we don't need to write that. So we don't have anything to worry about. Even roots, we do not have any roots here at all. So again, we don't have anything to worry about. So that means our domain is just going to be from negative infinity to positive infinity with nothing to remove. So that is our domain, okay? So that's how we do it algebraically, finding the domain. Okay, so this one, since there's no even roots and no denominator to worry about, it's all values of x. All right, so this ends CPM Precalculus Chapter 2, number 89.